Electric fields are great and all, but as it turns out, they're not the only kind of field relevant to E&M. A long time ago, people noticed that certain rocks interacted with certain metals in mysterious ways. This and other similar phenomena were referred to as magnetism, which was in turn attributed to a magnetic field, which we now indicate with a B. Today we know that magnetic fields basically come from three kinds of sources. Some magnetic fields come from permanent magnets, which as it turns out are extremely difficult to treat mathematically, so we won't dwell on them today. Some magnetic fields come from time-varying electric fields. That's part of what's called electromagnetic induction, which we'll talk about later. And the easiest kind of magnetic field to do the math for is the magnetic field that comes from moving charges, also known as currents. Electric currents produce magnetic fields. If you've ever heard the term electromagnet, that's what that's referring to. Okay, so electric fields come from charges, and Coulomb's law tells us how bits of charges make bits of field. The Biot-Savart law is the corresponding law for magnetism. It tells us how bits of current make bits of field. A lot of it is structurally just like Coulomb's law. There's an R vector out here that points from the source to the observation point. There's an R cubed in the bottom, a source term, and a constant that makes all the numbers work out in a particular system of units. In SI, mu naught, sometimes called the permeability of free space, is equal to 4 pi times 10 to the minus 7th with some units. And yeah, it's a little weird that our constant involves a 4 pi over a 4 pi, and there is a story behind that, but it's a bit of a tangent, so we won't worry about it here. The magnetic field itself, when working in SI units, is measured in teslas, indicated with a capital T. 1 Tesla is a fairly large unit. The Earth's magnetic field, for example, is on the order of milliteslas, and MRI machines that make really big magnetic fields give you something on the order of 1 or 2 Tesla. Now, there is one major way in which the Biot-Savart law differs from Coulomb's law. Instead of coming from dq's, which are scalars, magnetic fields come from currents, which have direction. The source term in the Biot-Savart law is this goofy IdL thing, where I is the magnitude of the current going through a wire, and dl is a little differential bit of the length of the wire carrying the current, where the dl points in the direction that the current is flowing locally. Finding the total magnetic field made by a current-carrying wire involves breaking the wire into bits and adding up the effect of all the bits with an integral. The fact that the source term is a vector complicates things. Rather than just multiplying the IdL by an R vector, we do a cross product of dl with R. Let's recall a couple basic facts about cross products. First off, if you cross together two vectors A and B that are separated by some angle theta, the magnitude of the result goes like AB sine theta. And from this we see that crossing parallel vectors gives 0, and crossing perpendicular vectors gives the maximum possible. Second thing to remember, a cross product takes two vectors as inputs and makes a third vector as an output. Their directions are related by the right-hand rule. There's a bunch of different ways to express the right-hand rule, but the way I like best is as follows. Given that A cross B equals C, I take my first finger, which is the index finger if I'm counting on my fingers in most North American countries, and I put that along the first vector. Then I put my second finger, the middle finger, along the second vector, and I stick out my thumb to get the direction of the result. Note that this only works correctly if you use your right hand, and note that right-handed people sometimes absent-mindedly use their left hand if they have a pencil occupying their right hand, so watch out for that. We'll do an example of a Biot-Savart law calculation soon, But for now, let me summarize a couple results that also have right-hand rules associated. We'll find that a long, straight wire makes a magnetic field that points around it in circular loops, with the direction of the loop coming from the right-hand rule. Take your right hand, put your thumb in the direction of the current, and curl your fingers around. That's the direction of the magnetic field. We'll also find that a coil of wire makes a field that's pretty complicated in general. But if you're looking right at the axis of the loop, it points straight. To find out which direction it points, wrap the fingers of your right hand around the coil in the sense that the current flows, and your thumb will show the direction of the field. And just FYI, in actual practice, coils of wire are probably the most common configuration. You'll see them in generators, electric motors, electromagnets, MRI machines, all sorts of other stuff.